Welcome to a discussion regarding scattering regimes of waves using computational electromagnetics. My name is Rahil and today I will be your host. How do you think the photograph of this molecule was taken? A team of IBM scientists captured the first close up image of a single molecule in 2009. This molecule is graphene, and these green smears are bonds. Clearly, we can't see this with our naked eye. This just goes on to prove that wavelength of light in the visible spectrum can't resolve this image. You can fit 500 of these molecules in one wavelength of blue light. That is like a huge truck hitting a small can. It's just going to run over it. So, what can you do? Take small ping pong balls and reflect them off the can. This is basically what was done. The graphene molecule's image was taken with the help of a scanning electron microscope, which has a resolution of zero point 0.5 nanometers. Now I have run some simulations using meep. Meep is a free software which uses electromagnetic simulation via the FDTD method to show us how the wave propagates. I know it's a lot of big words to take, so let's digress a bit. The study of electromagnetics revolves around Maxwell's equations, and the wave is anything that basically satisfies the four equations. Finite domain time difference is the simplest, most widely used computational electromagnetics method. It basically involves discretizing the computational domain into steps of space and time such that they satisfy some stability criterion and allow for propagation of the wave. meep uses a language called scheme. Let's walk through the code of the simulations. Now, the first line, reset meep, it reinitializes meep. Basically removes the previous structures. Now the second line, that is set geometry lattice. This sets the computational domain, basically y cross x cross z. No size in z means it's a 2D program. And 16 to 16 basically says it is a 16 to 16 grid. And the units here are micrometers. In meep, the units are a bit different. I suggest you learn by the references I've given at the end of the video. Now, in set geometry list, make block is basically my object which is at 2 0 with a breadth of 0.5 and length of 0.016. That's basically 0.01 lambda of the source that I've given. Now, infinity here states it's just a 2D program again. And I have made epsilon infinity because this is a perfectly electric conductor. I've chosen a PEC because I want to see the reflection and diffraction better. Now, set PML layers, these are perfectly matched layers of thickness 1.0 so that they absorb the scattered waves and there won't be any reflections from the boundary. So resolution equal to 10 is basically dx, that the space step which is lambda by 10, or the, and I have not made it 20 because it's taking a lot of time computationally. And this is basically the source which has a wavelength of 0.5 into square root of 11, which is 1.658 micrometers. And width 20 basically says it is a wave that's slowly building up, or rather it corresponds to a tan h turn on function, so that the source slowly turns on with time. And it's at run until 200 basically means it runs for 200 periods of the source. And at the beginning, output epsilon basically shows how the computational domain is modeled and shows where the object is. And to append ez, that is basically the now, as you can see, the length of the object here is 0.01 lambda. That means it's 10 raised to minus 2 times lambda, which means it's pretty small compared to the wavelength of the source. And in the next is exactly similar to the first one, but I've changed the length of the object to 0.16, which is basically 0.1 times lambda, and then I made 0.5 times lambda, and so on. I've increased the size all the way till at 3 lambda. I've increased the resolution to 20 because I want to check how much time it would take. And at I've increased all the way to 10 lambda, but that takes 16.5, which was higher than the 16 cross 16 grid. So I've made it a 25 cross 25 grid for that purpose. And now we look at the structures of the object. Basically, this is how the computational domain is with the object sizes. And as you can see, this is how they are modeled. Now let's look at the simulations. Now as you can see, the waves are slowly building up in all of them. This is basically the tanh hyperbolic turn on function that I've been talking about. And then as you can clearly see, at L equal to 0.01 lambda is basically the truck can analogy, where the truck is the wave and the can is the object. While at L is equal to 10 lambda, it's exactly the opposite, where you have the ping pong balls being the wavelength and the object being the can. Now what are we looking at here? Now at the steady state snapshot, we can see that we are seeing reflection and diffraction of waves. There is no refraction as in here, as in because the objects are PEC, that is perfect electric conductors. Now at L equal to 0.01 lambda, the wave barely realizes the object and propagates as if in vacuum. At L equal to 0.5 lambda and lambda, diffraction is seen, that is, wave tries to bend around the object. And at 3 lambda and 10 lambda, the wave almost follows a ray-like path, as in it looks like a ray-like solution. So these are the three different regimes that I've been talking about. So these are the results I've gathered from here. The three scattering regimes are the size of the object being L is equal to from 0 to 0.5 lambda, we have a wave as in vacuum. And from if L is equal to 0.5 lambda to 3 lambda, we have a wave with diffraction, that is L is comparable to lambda. We can see all these Huygens principle and things like that, where you have the wavelets being produced from slits and things like that. L is equal. These are the references. I have linked them down below. And thank you for your patience.